at, right, we are looking at what we call the moduli properties. And these moduli properties are very, very important properties that we need to learn, and they actually need to be proven. So the question is, in other words, here we're saying the modulus of a quotient is the quotient of the moduli. The modulus of a product is the product of the moduli. How do we actually prove this? And we proceed to demonstrate a proof actually of this as follows. Right, so we start by realizing that first things first, these results themselves can be proven. Now, to prove this one, we square the result first things first. Okay, sorry, but we use a very, very well-known result. So we need to note. We use a note that if z is x plus iy, and this is a complex number, then by definition of the modulus of z is x squared plus y squared square root. And why is the modulus like this? Okay, why is it this? It is the definition of the modulus. So it's nothing that we are inventing here. It's not an invention. It is just the definition of the modulus of z, because if z is x plus iy, its modulus is the square root of x squared plus y squared. Okay, what about if we square both sides of this? We square on the left, but also we square on the right. It means that the modulus squared is going to be x squared plus y squared. Like this. So the modulus of z squared is x squared plus y squared. But there's something that I want us to discuss actually as well, because z times the complex conjugate of z. Okay, z is x plus iy, but its complex conjugate is, okay, you can first write x plus iy and then put the complex conjugate like that, so that you have x plus iy, and then the complex conjugate of this is x minus iy. Just commenting on the notation of the complex conjugate. Right. So what do we do now? We multiply these things. Okay, this is like a difference of two squares, so it's x squared plus y squared. In other words, a complex number times its complex conjugate is just the square of the real part plus the square of the imaginary part. Okay, but this is not new, because also the modulus of z squared is x squared plus y squared. I mean, hence, the modulus squared is the same as this. The modulus of z squared is the same as z times the complex conjugate of z. Hence, thus. Okay, we use that to prove and to establish these very important results. Okay, now division and multiplication mathematics are inverses of each other, and now they really are very important. But yeah, if you can prove something for products, yeah, there are implications for quotients as well. Okay, let's start with the products. But to deal with the product, we'll square these. We'll square these. Okay, if we square these, then it is the same as what? According to this law. Okay, if you square the modulus, it's the same as that complex number times its complex conjugate. Okay, so that's what we're going to use. So it is the complex number multiplied by its complex conjugate. And therefore, this is Z1 over Z2, Z1 bar over Z2 bar. Z1, Z1 bar, Z2, Z2 bar. Okay, like this. But what is the meaning of this? Now, here, if you have Z1 times Z1 bar, it is the same as what? Okay, it's the same as the modulus of Z1 squared because of this. The modulus of Z squared is the same as Z times Z bar. Okay, we established that one. But also here, when you have Z times Z bar is the same as, obviously here it's Z2. Z2 times Z2 bar is the squared. Hence, Z1 over Z2 squared is Z1 modulus squared over the modulus of Z2 squared, like this. Okay, now, what can we do with this? What can we actually do now with these things here? Okay, but this thing here can be written up. If you square something like this, you square this, you square that, it is the same as modulus of Z1 divided by modulus of Z2 squared. And this means that Z1, Z2 is Z1, Z2. Okay, so, okay, what have we proven? We have proven that the modulus of a quotient is the quotient of the moduli. Okay, we're going to use these things when do integration, contour integration. Okay, it's going to be our next point. And then now let us prove the products. Let's prove the products. Note, I'm mentioning in passing that the modulus of a product like this is the product of the moduli like this. Rather, the complex conjugate of a product, okay, complex conjugate of a product is the product of the complex conjugates. But also, the complex conjugate of a sum is the sum of the complex conjugates. The complex conjugate of a difference is the difference of the complex conjugates. Okay, so these are some of the properties that we shall be using very, very often. And we shall be using these. But now let's prove the product law of the moduli, of the modulus. In other words, if you have Z1, Z2 modulus, what is this? Well, it is the product of the moduli, but let's prove this. But to prove this, we square these things. Because if you square these, then we can be able to write this. And then we have this. These are products, they're not differences, in case somebody thinks. So if you have the square of a complex number is the same as that complex number times the complex conjugate, which is Z1, Z2, Z1 bar, Z2 bar, which is Z1, Z1 bar, Z2, Z2 bar. What is Z1 times Z1 bar? Okay, we've already seen that this one is the modulus squared of Z1, the modulus squared of Z2, Z1, Z2 squared. Okay, now what is this? Z1, Z2 squared, Z1 squared, Z2 squared. Okay, so you can take the square roots both sides. If you take the square roots both sides, this becomes Z1, Z2, Z1, Z2. So we've been able to prove that the modulus of a product is the product of the moduli. Yes. The modulus of a product is the product of the moduli. Okay, just a note there. Now let us just and what about for the sums? Okay, what about for the sums? Now, okay, these proofs are not only this. This is not the only method. Okay, let me demonstrate another proof of the products, for example, and the difference. Okay, proof. This one. Z1, Z2 is Z1, Z2, like this. So we need to prove this one. Okay. How do we prove this? Okay, to prove this, we let Z1 be X plus, okay, Z1 be X1 plus IY1, Z2 be X2 plus IY2. And then now we come and use it here. And if we use it there, we start with one side. So we're going to have the left-hand side. And then want to prove is the right. So this is the complex conjugate of a product. So you can just break the complex conjugate of a product and take the complex conjugate of each of the factors. Okay, now let's take the left. You can take one of them. Okay, let's just take the left. So we're going to take this part. And then the Z1 is X plus I, Y1. Z2 is X2. Okay, this is X1. Okay. This is X1. This is X2, YY2, IY2. Okay, so now what we do? You take this and then you multiply everything underneath, which is X1, X2. That is one way that's the method we use. X1, X2, and then multiply X1 times this, which is plus X1 IY2, but we can write it nicely. Normally we start with the I. So multiplying X1 and the IY2, you can write I, then X1, Y2. Then here you put I, X2, Y1. And then here you put minus Y1, Y2. Right, so this is what we get. And then now we continue with now we need to do the grouping. So in other words, you'd have the left-hand side. Okay, so the left-hand side now underneath this, okay, it's still, okay, yeah, you can write Z1, Z2 complex conjugate, and you have the left-hand side, and then it is X1, X2 minus Y1, Y2, which is X1, X2 minus Y1, Y2, Y1, Y2 in parentheses like this, plus I into, and then here we have X1, Y2, X1, Y2, X1, Y2, and then X2, Y1, X2, Y1, and then you have this. Okay, then you have the left-hand side. Okay, now we have been able to write this number, the complex number, the square root in terms of real part plus ideal imaginary part. So, which is X1, X2 minus Y1, Y2, which is minus I, X1, Y2 plus X2, Y1. Okay, so obviously if you take the complex conjugate of this big number, it is just that you need to just change the sign of the I to the opposite. It was plus I, so it becomes minus I. And then now we continue with our expansions and other things. And so what do we get out of this? So this one here becomes x1, x2 minus minus y1 minus y2 and then okay, and then here we're getting, okay, because this is the same as this. If you put minus minus here and then three minus signs, then they give a minus. If you multiply them, then here would have the minus y1 x2. Okay, you put here and you put minus y1 x2 plus x1 minus y2, like this. So okay, this is what we have. And then this is the same as this. Now, but we can be able to factorize this into x1 minus I y1, x2 minus I y2. Okay, so this one can be factorized into this. Okay, if you factorize it like this, is the same. This is the same as z1 complex conjugate, z2 complex conjugate. Okay, what have we been able to establish is that the complex conjugate of a product is the product of the complex conjugates, and hence the complex conjugate of a product is the product of the complex conjugates, like this. Obviously, there are a couple of things that we want to establish, and those proofs want to establish, but also let us draw some graphs, sketch the following. Right, sketch the following, and then we shall review it. Okay, we're interested in doing everything, but time is always the factor. Yeah, so sketch the following. So in A, we need to sketch the real part of the complex conjugate minus I equals 2. Okay, so want to sketch this one and want to see how we can sketch this. But also want to sketch part B, where this is 2 complex conjugate plus I, which is 4. And then now we have this solution here. So in other words, what are we supposed to have here? So you have the real part of z minus I equals 2, which is the real part of z. What is that? Well, in mathematics, wherever there is z, we have a tendency of putting x plus iy. So we understand, therefore, here that z is x plus iy. So we want to sketch this relation, this equation. So we write the real part of z bar minus I. Wherever there is z, you put x plus iy. Then put the minus there. Okay, so you would have the real part of x minus iy minus I. So, and then we have the real part of x, and then if you have the minus I here, which is 1 plus y plus 1. Okay, so now we want to take the real part. What is the real part of this? Well, the real part of this is only the x. Well, in essence, then it means that if you have z bar minus I equals 2, this is just the same thing as x equals 2. Okay, so we have that the real part of z bar minus I equals 2 is the same as x equals 2. Let us sketch this. What is the graph of this? How does the graph of this look like? Okay, the graph of this will be formed by the imaginary part at the top and then the real part at the bottom, and this is called the Argand diagram. Right, so this one is real part of Z, real axis, and this one is the imaginary axis. Okay, so if x equals 2, then it's like a vertical line through 2. Right, so the vertical line through 2 is what is of interest to us. Right, so a vertical line through 2 like this. So this one is the same as x equals 2. Right, x equals 2. Right, so if x equals 2, okay, this is the same as saying the real part of z is 2. All right, so yeah, this is the graph of that. So yeah, we need to just sketch a little bit some of these things. But now to sketch, normally we just replace x by the x plus iy, and then be in a position to do the sketching. But let us look at another sketch, for example. Part B, want to sketch this one. The modulus of 2 times z bar plus I equals 4. Right, so the modulus of 2 times z bar plus I equals 4. And therefore, this one here is 2 into x plus iy which is x plus iy. Okay, plus I. Okay, z is x plus iy. Okay, want to sketch these. So to know what kind of a shape this is, we write it in terms of x and y. Okay, so that we can, because that is what we learn first. And then this presentation of complex numbers is relatively new because in school we learn real numbers first, in real functions. So this, the complex conjugate of this is x minus iy plus I equals 4. Distribution is 2x minus 2yi, or minus 2iy plus I equals 4. Right, B, which is the same as 2x minus 2iy, okay, minus 2iy plus I equals 4. Okay, so which means therefore we have 2x plus I, and therefore this is minus 2y plus 1 equals 4, like this. And so what then do we do now with this? Right, so what we can do with these, we are able to write it as the modulus is the square root of 2x squared minus 2y plus 1 squared. And this is 4. And you square this, it becomes 4x squared plus. Okay, you square both sides. It becomes 4x squared, and if you square 4, you get a 16. And you square this one, it becomes 4y squared minus 4y. Right. Minus 4y plus 1. Okay. So if you have the part B, 4x squared plus 4y squared. 4x squared plus 4y squared. Minus 4y plus 1. Minus 4y plus 1 is equal to 16. So which means that you have 4x squared plus 4y squared minus 4y, and this is equal to 15. Okay. fine, but yeah, we can do it nicely. Right, you can do it very, very easily. Let's make it easy. That I've just made it a bit too complex. We're gonna move in circles, but let's just avoid that. So yeah, I'm just gonna do something easy. And I'm just gonna look at the square root of this. And just yeah, square root of 2x plus, then you have minus 2y plus 1. Okay. And then what are we getting here? Okay, and then if we square both sides of this, you get 2x squared minus 2y plus 1. You square this, it's 16. Okay, this is like this. And if you square this, it becomes 4x squared plus. Okay, here we can factor out minus 2. And then you have y minus 1/2. Like this, which is 16. Which is 4x squared plus 4. Y minus 1/2 equals 16. Part B, which is 4x squared, which is plus 4. Y minus 1/2 equals what? 16, yes? Okay, you can divide through by 4, getting x squared, y minus 1/2. Okay, we're trying to simplify it to something that we know. Okay, we have 16 out of 4. Something that we know from school. Normally this comes from school, the basic shapes, and then we have 4. So this obviously because the coefficients are 1, 1, it becomes a circle with center 0, that, and radius equals the square root of 4, 2 units. Okay. Yeah. So yeah, to get the radius of the circle, we take the square root. Okay, let us draw this thing here. Okay, but obviously because this one it has 0 component, so yeah, it's like x minus 0 squared plus y minus 1/2 squared equals 4. So yeah, that kind of thing. So this 0. Let's look at the next. Okay, let us clean this up. Okay. Okay, so now, okay, to understand this, then x is 0 and y is half. X is 0 and y is half. What point is this? Is this one? X is 0 and y is 1/2. So you can see this as I over 2. Okay, you can write it like that. But you can write it as 0 and 1/2, same thing. But this axis is imaginary z, and this is x-axis and imaginary real number, real axis. Okay, this one is the set of all the real z. So it's the real axis, and this one is the imaginary axis. Okay, so right, with that said, then we continue and we're gonna look at the circle centered at this point, but yeah, radius 2. Radius 2 from 1/2, 2. If you add 2 to a half, you get to what? Okay, so you have 0.5, 2.5, you add 2, you get 2.5. And this one, 2.5 is like 5 over 2i. And this one, you 2 down here, you get to minus 3i out of 2. Because it's a full circle, that's fine. Because it's a full circle, then it's going to be like so. It is a circle, forgive. We're not drawing a perfect circle, but yeah, it is this shape that we have. Okay, so that is something that you need to take note of. And I want us to discuss some other things as well. As we are discussing this, there is something that remains very, very important. So I want to mention in passing something called connected. Connected set. A set. A set E, which can, let's start with a subset of the real numbers, is called connected. A set E is called connected if there does not exist. If there does not exist two open disjoint sets such that okay, so let's first understand what is happening here. First and foremost, we're saying this set E is called connected if there does not exist two open sets or two open disjoint sets. Let me just call them A and B. Disjoint sets A and B such that A intersection B is the empty set. And the E, for example, can be written as the union. So, yeah, A union B. Okay, this set E is called connected if you cannot find two open sets so that this is the case. So E is connected if you cannot have two open sets that separate. Okay, we use the word separation because they are so they are sets that observe separation. Okay, so in other words, this set is connected if you cannot find two open disjoint sets A and B such that their intersection is empty, so that their intersection is empty. Let's make it empty. Just 1 minute. Okay, let's make it empty. So this set is called connected if there does not exist two open disjoint sets A and B such that their intersection is empty. So you can't find sets that are disjoint because the word disjoint means they have no intersection. And this set is the union of such sets. So the set is called connected if you can't have this. That is the point. So yeah, just take note of that there. Okay, and I want to, I'm going to mention a little bit more. Okay, we continue. Right. Right, so that set is called connected if you cannot break it into two disjoint open sets that are like that. Okay, we'll continue, please. I'll continue, please. Okay, right. I want us to look at a couple of other things that are very, very important for us to consider. And that are things that will be studied very, very much. And we need to make sure that we sort of understand these. And it is exactly, okay, the following. And we discuss some of them, but I want us to discuss a little bit more of the results that are very important. Right. The exponential form, we have discussed that, but let us look at results that become extremely important and that relate to the exponential form and other things that are very, very essential to us. Okay. The argument function. Right. We note, therefore, that, for example, the argument of a complex number z1 divided by z2 is the same as the argument of z1 minus the argument of z2. If you divide two complex numbers, if we divide two complex numbers, that is what we get there. Okay. All right, so we continue. Right, there are still several things that I want us to sort of obviously take note of here. Okay. So now we note, therefore, that the argument, okay, of z1, the argument of z1, z2 is the argument of z1 plus the argument of z2. Okay. So yeah, just to take note of this. Okay, now let us give a small example. Just gonna be very brief, time-wise. Okay, so for example, if z is I over minus 1 minus I, for example, we can be able to note that the argument of z is the argument of the quotient, or this rational expression, I over minus 1 minus I. And then this is the argument of I minus the argument of minus 1 minus I. Okay. Right, so the question then is, and I want us to discuss this very carefully. There's something called the principal argument of I. So I'm gonna,
Hello?
okay, yes, please.
The lesson's gonna end.
Yeah, it's ending now. All right. I can